Hello everyone. Today we'll be starting a new topic, which is gravitational fields. And this topic will involve Newton's law of gravitation, all the gravitational forces, and it also connects to circular motion as well. So I hope you will enjoy this topic. Now, to start off, let's try to explore what the meaning of field is. So when you hear about fields, what even is a field? So we say that a field is a region of space where a body with certain properties experiences a force. So you have learned many types of fields, right? There is electric field, there's gravitational field, there's magnetic field. So for example, when we talk about electric field, you have a positive charge, maybe here, and then you have a negative charge maybe over here. Obviously, both of these are attracted to each other. So the space around here is called the electric field. So similarly, when we talk about gravitational fields, it's the space whereby a mass, so let's say you have something over here and this is the ground, so we call this a mass. So this can be any object where the mass experiences a gravitational force, so the force of gravity acts downwards. So this is the gravitational force. Now this actually brings us to a very important concept, which is, why does the mass experience a gravitational force, or why is it that it goes downwards and not sideways maybe? What causes this force exactly? So to answer this question, we use Newton's law of gravitation. And what is Newton's law of gravitation? So Newton's law of gravitation says that the force between point masses is directly proportional to the products of the two masses and inversely proportional to the square of their separation. Now that looks complicated, but let's try to understand this with this diagram over here. So let's say you have masses over here, which is m1 and m2, and they are separated by a distance r. Now Newton says that both of them will have a force. So m1 will experience a force which will make it attracted towards m2. Let's call this f1. And m2 will also be attracted to m1. Let's call this force f2. So you can see that both F1 and F2 are Newton's third law pair, because the force over here is the same as the force over here. That's what Newton says. That when you have two masses and they're separated by a distance r, both of them will experience a force. And these two forces will be attractive towards each other, and they are Newton's third law pairs. So you can see that this one is going to the right and this one is going to the left. And this is where the formula comes in, which is F equals to G m1 m2 over r square. So the gravitational force F1 or F2 can be represented by this formula, which is G, which is the gravitational constant, and this will be 6.67 times 10 power negative 11. m1 is the mass of the first object and m2 of the second object, and r squared will be the separation between these two objects. There is also a relationship which is very crucial in this topic, and this is one of the main ways to answer questions regarding gravitational fields. And this relationship is this one, which is Fg equals to Fc. So let me explain this. Let's say you have Earth here, and you have something which is moving around, right? Now you know that the Earth and the mass will experience the force, and this force will be the Newton's law of gravitation. So this mass will experience a force towards the center of the Earth, which is the gravity, right? So the Earth is mass 1, and this mass is mass 2, and they are separated by a certain radius r. By the way, when you are doing this, the radius is between the center of the first object and the center of the second object, and that's why they are called point masses. So in the formula, it's assumed that you are talking about the center of an object. So when you have this force over here, which is pulling it towards the center of the Earth, we learned in topic 1 that the force which makes you move around in a circle and is directed towards the center is called the centripetal force. And centripetal force must be provided by something. It just can't appear out of nowhere. And in this case, gravitational force is the one which is providing the centripetal force. And this is very crucial, because what you can do is that you can form another equation then. So if you have gravitational force providing the centripetal force, And we know the formula for gravitational force, which is G m1 m2 over r square. And we know the formula for centripetal force. So remember, centripetal force had two formulas. You had mr omega square and you had mv square of r. So you can use either of those. Let's say mv square over r. Then you can see that one of the mass will cancel out. So let's say this one is m2 and this one is m, so the m and the m cancels out. This m2 can also be written as small m, by the way, because we're talking about the mass of the same object here. Then the radius as well can cancel out because you have r square over here and you have r over here. So this r can cancel out and one of the squares goes out. So you are left with gm over r equals to v square. You see, so you can actually get different values of quantities using this equation, and you can play around with this equation to answer the questions. You can also use mr omega square over here, and you can also form a different formula. So all these are just techniques and short tips on how to solve the questions. Okay, now we continue to another part of this topic, which is the gravitational field strength. And the gravitational field strength is defined as the force per unit mass, right? So which specific force? This is the gravitational force per the unit mass. Now we know that the gravitational force is equal to gmm over r squared, right? So when you plug that formula into this, you get gmm over r squared with this m over here. Now these two m's cancel out, so I'm supposed to write small m here. These two m's cancel out and you are left with gm over r squared. And this will be your formula for the gravitational field strength. And the units can either be written as Newton per kg or meter per second square. And you might be realizing that meter per second square is acceleration as well. So when we are talking about gravity or acceleration due to gravity, that's actually the gravitational field strength. Why is that? Because, for example, let's say this is the Earth, and you are at the surface of the Earth, right? So you are over here. And this is the center of the Earth. There is obviously a separation between the center of the Earth and you at the surface of the Earth. There is the mass of the Earth, m1, and there is your mass, which is m2, and this is the separation, which is the radius. Now, according to Newton, there will be forces exerted between this mass and this mass, and this force exerted will be the gravitational force. Now, the gravitational force per unit mass is the gravity. So if we talk about Earth, because the gravity is 9.81 Newton per kg, it means that for every 1 kg, there is 9.81 Newton force acting on it. So that's why if something has a higher mass, it will have more force acting on it. And that's because of Newton's law of gravitation. Now, you might ask, let's say this is the surface of the Earth, right? So I'm zooming in on this area exactly. If I just zoom in on this area, let's say this is the Earth, this is the surface, and maybe you have a big building and you have a ball falling from that building. This is the surface of the Earth, so this is where this line is over here. This is the surface, and there is also an additional distance, maybe let's call it h. So you might ask, then maybe the gravitational fields won't be the same. It will be less or more, because when we talk about the formula for gravitational field, this is gm over r square, but the radius now will be more because you have that original r, which is from the center of the Earth until the top, and you have this additional h. But in reality, because this radius is so big, the difference between the center of the Earth and the surface is too huge compared to this h over here. So for example, h might even be maybe 100 meters. But the distance from the center of the Earth until the surface is too huge. It might be 1 times 100 times of this thing. So because this r is too huge, you don't keep the additional h in the formula. So to make this more clear, I won't keep g equals to gm over r plus h squared. Like this additional h is negligible. So that's why you just keep normal r squared, which is the difference between the center of the Earth and the surface of the Earth. Now it's time for a small tip again for your exams. Usually they ask how the gravitational field strength differs with radius. So you might be given a graph, let's say like this, whereby in the y-axis you have the gravitational field strength, and in the x-axis you have the radius r. Okay, so you start with r here, then they'll give you maybe 2r, and then 3r, and then 4r. And they want you to know how does the graph of g change with r. Is it a straight line like this? Is it a curve? Is it a curve going downwards, or how does it change? Now, my one tip to you is that whenever you are drawing graphs, always look at the formula and the relation between these two elements. So what's the formula for gravitational field strength? G equals to gm over r square. G equals to gm over r square. You can see that we have g here and we have r here. I think I should correct this. You have g here and you have r here. The relation between these two is that g is inversely proportional to r square, right? This was your first step, to identify the formula and then to identify the relationship between these two elements in the formula. Whenever you have an inverse proportion, that means that the graph is going down. So it's either a straight line going down or it's a curve going down, right? Now, when you have a square here, automatically it means it's a curve. So you will notice that this here, this is at the surface, right? Because r was at the surface. This will be 9.81. And because it's a square, it's going down, right? So when you increase this by 2, when you increase the radius by 2, so you're going from r to 2r, how much will your g change? If you increase this by 2, the gravitational field strength decreases by 2 square. So when you increase this by 2, this one decreases by 4. Why is it 4? Because there's a square over here. So even if you increase it by 3, then it will be 3 square, which is 9. I hope that makes sense. So for the 2r, the point that we will plot will be 4 times less of this. So you'll do 9.81 divided by 4, which comes around maybe 2.2 or something. And your next plot will be somewhere over here. Then again, when you increase this by 3, so when you go from r to 3r, this will decrease by 9. So you'll do 9.81 divided by 9, and that will come around something 1, right? So this will be somewhere over here. And doing the same process again, you'll see that this graph is a curve which is going downwards like this. Let's look at gravitational potential energy now. So the way this is defined is that this is the work done to bring a mass m from infinity up to a point. So you have the gravitational potential energy expressed as this U symbol, and it's the work done to bring the mass m from infinity to a point. So the only difference between this formula and that one is that now we have a negative sign, and instead of r squared, now we have an r. So this is the difference. And how do we form this formula? To be honest, the formation of this formula is complex and requires a lot of mathematics knowledge. But just to give you a glimpse, the formula is formed from doing the integration of this graph over here. So the area under the graph is how you get the gravitational potential energy. So for example, you can take this part here, and you can take this part here, and you can integrate this to get the area. And that's how you get this formula over here. But you don't have to know how this integration is done and how this formula has been made. But the crucial thing to know over here is that this is actually negative. The gravitational potential energy is negative. And why is that? Now, let me try to explain to you one concept in physics. For example, when you have one mass here and you have another mass here, and they're both attracting each other, do you have to keep any effort to attract them? You don't, right? This is just automatic, and they're without any effort, both of these will actually attract over here. So you're not doing any work. This is just automatic. It's happening because of nature. But when you have two masses which are attracting each other and you pull this away, now imagine you're trying to pull this away. You have to do some work, right? You have to force it. Like you're opposing the nature. Now this is what actually work done means. Work done is when you try to do something which is not normal. Like you try to oppose it. For example, you have a normal car over here and you're moving this car. This car, the normal behavior of it is to be stationary. But when you start the engine is actually pushing it to go this way. It's doing some work, right? It's doing some useful work there. Now, for gravitational potential energy, because this force is attractive, and the way gravitational potential energy is defined is that the maximum one, the maximum value of U is 0. So this is just how it's defined, that the maximum gravitational potential energy is 0. And the graph of it looks like this. So I'm trying to go a bit deep here, but I'm trying to explain to you why this is the case. So we have U in the y-axis, and we have R in the x-axis. And this is the maximum gravitational potential energy when these two are completely far from each other. So imagine how much work you have to do to oppose these two masses, right? And this is at 0. So the maximum radius is when you will achieve the greatest work done, and the greatest work done is when it's at 0. And below it, all of it will be negative. So the graph of it looks something like this, right? So as you try to separate these two things away, you have to do more and more work to separate them. And that's why there's a negative sign over here. Now we continue with gravitational potential. And the way we define gravitational potential is that it's the work done to bring a unit mass from infinity to a point. So the only difference between the gravitational potential energy and gravitational potential is literally just the word unit. When we say unit mass, we just mean that it's divided by the mass, right? So you do the gravitational potential energy divide by a unit mass, so mass, right? And this is the formula which you get for gravitational potential. And this one is represented by as phi. Okay, so this is the unit for representing the gravitational potential. Alright, so now we'll look at how we can get the kinetic energy of a mass, right, which is moving around in orbit. So let's say you have the Earth's surface over here, and then you have a mass which is moving around the Earth's surface. We know that we have a gravitational potential energy which is going towards the center. So we have GPE, but also we have kinetic energy of this mass which is moving around in this orbit. Now, what is this kinetic energy? Remember, we said that GPE is the gravitational potential energy, which is the one which is making it go towards the center of the circle. So we say that Fg equals to Fc. You guys remember this relationship, right? So Fg was G over R square, and Fc was mv square over R. Then when we cancel this, we cancel this, we cancel this, we cancel this, you are left with v square equals to gm over R. And then we can actually get v as square root of gm over R. Now, why did I do this? Why did I calculate v? This is because the equation for kinetic energy is half mv square, right? So kinetic energy equals to half mv square. So we can plug this v over here into this equation, and we can get the equation for the kinetic energy. So we get half times m times, you can just use the v square, which was this one, gm over R, times gm over R. So we find out that the kinetic energy is given by gmm divided by 2R. And this in fact is positive, right, compared to the gravitational potential energy, which was negative. So just to recap, GPE was equal to negative gmm over R, and the kinetic energy is gmm over 2R. So based on these two equations, we can actually get the equation for the total energy. So the total energy will be the GPE plus the KE. So this is equal to negative gmm over R plus gmm over 2R. So just doing the subtraction of this gives you negative gmm divided by 2R. And this will be your equation for the total energy of an object moving around an orbit. Right, so now just putting this into a graph again. Let's take the same graph as before, the one we drew for the gravitational potential energy. Remember the graph of gravitational potential energy was that when you are at r over here, you have negative gmm over r, and you have a highest possible value at 0, which we said was infinity. So this was the line for it. And now, how about the kinetic energy? So this is the GPE. And how about the kinetic energy? For the kinetic energy, again, this is the relationship. KE equals to gmm over 2r. You're drawing the graph of energy against the radius or the distance. So energy against the radius. You see that they are inversely proportional, right? So energy is inversely proportional to r. Now, if it's inversely proportional, it means that the graph is going to go down. It's going to decrease. And in inverse proportions like this graph is decreasing with a curve, right? So the graph actually decreases as a curve like this and not as a straight line. So you will see that the graph will go something like this, right? So this will be the kinetic energy. And we can get the total energy graph as well. So if this is gmm over 2r and this is negative gmm over r, we have the total energy as negative gmm over 2r. So it will start somewhere around here, and the graph of it looks something like this. Okay, sorry for the bad drawing, but I hope this makes sense. I just added these two graphs and got this curve in between. Okay. Now there is this concept of escaping an orbit. So let me show you with an example. You see over here, we talked about this object moving in this orbit of the Earth, right? And obviously there's a distance between the center and this object. Now, how far does this object have to be to completely escape this planet? Let's say this is Earth. Okay. Let's say this is planet Earth. Now, how far does this object have to be to completely escape the Earth and escape its orbit? So this point is actually defined as the point where the total energy becomes 0. So when the total energy becomes 0, this is the point where it has completely separated. To go back to the earlier example, remember when we said that when u equals to 0, this is when you have done so much work up to the point that these two are completely separated. So when the total energy becomes 0, this is called the point of separation, and we can assume it will be somewhere around here, right? So when x becomes infinity, then the total energy becomes 0. So total energy equals to 0. This is where the point of separation will be. And in your CIE exams, what they ask you is to find out the speed of this thing. So what will be the velocity of this object to escape a planet or to escape the surface of the Earth, right? Now, what you can do is to find out what is actually needed for this object to escape. So going back to this GPE graph, you can see that for you to escape, you need the GPE to become 0. It has to go away from this certain distance. So you can see that this difference in GPE is how much work you have to supply. You have to put in effort to go from here until here. And this effort is given by this kinetic energy. So you can say that the change in GPE is the work done or the effort put in by the kinetic energy. So change in GPE equals to the kinetic energy. So how much kinetic energy do we have to provide? So the change in GPE is what? The final minus the initial. The final will be 0, and the initial one is represented by negative gmm over r equals to the kinetic energy will be half mv square, right? Just the normal equations. Then this becomes gmm over r equals to a half mv square. This m and this m cancels out. So you are left with gm over r equals to v square over 2. Then bringing this here, you get v square equals to 2gm over r, right? And you will get your velocity as square root of 2gm divided by r. And this is called the escape velocity. This is the velocity that you need to escape from the Earth. Okay, so if a velocity of this one is provided, then an objects can escape away from the Earth. And of course, you can add that the minimum kinetic energy for you to escape will be a half times mass times v square, which will be 2 g m/r. So I remove the square root and you get 2 g/mm divided by 2r, which means that you get g/mm/r. So this is the minimum kinetic energy required for you to escape. The last part of this topic is regarding geostationary orbits. And this one is not a very critical part of this topic, but it does get asked sometimes, so I thought it's better to cover this. Now, a geostationary orbit is defined as an orbit which appears to remain above the same point on the Earth's surface at all times. So let me just show you this with an example here. Let's say you have this is the Earth, and then you have a satellite over here which is traveling. Now, let's say at this point of the Earth, this satellite is above it. You see, it's right above it. Then, after some point, because the Earth is rotating, the satellite will have moved, right? It will be going, let's say, now maybe it's over here. But it rotates with the Earth in the same speed. Like when, let's say, there is something over here, it's pointing to this, it's right above it. And then when it's rotated, that point which is rotated also rotates with the satellite as well. When this satellite moves, it moves in sync with the Earth. So when the Earth rotates, let's say 30 degrees, the satellite also rotates 30 degrees. When the Earth has completed a full rotation, the satellite has also completed a full rotation, right? So for it to have these features, it has to have a period of 24 hours because the Earth cycle is 24 hours. And the satellite also has to have the same one to stay in sync. If it is more, then it will not be able to stay in sync. It also has to go from west to east because the Earth also sets from west to east, and it has to travel in an equatorial orbit, right? So these are the three main features of a geostationary satellite. And that's it. That's it for this topic notes. There was a lot of formulas and graphs, and these are actually the main ones which will be covered in your exam. So please go through them nicely. And also don't forget to watch the past paper solutions of this topic because those are very crucial, and those will help you to get a proper understanding of this whole topic. Right. Thank you for watching.